motion of a body or a system of connected bodies displaced from a position of equilibrium. Free vibration is maintained by gravitational or elastic restoring forces, and undamped vibration are indefinite motions of a body or system where frictional effects are neglected. However, in reality, it is impossible because frictional force is present internally and externally. For our lab, it is a 2-degree of freedom system because it requires two independent coordinates to describe their motions. If we give suitable initial excitation, the system vibrates at one of these natural frequencies. During free vibration at one of the natural frequencies, the amplitude of the 2 degrees of freedom are related in a specific manner, and this configuration is called Mohd shape. So, 2 degrees of freedom system has two Mohd shapes corresponding to two natural frequencies. In practice, the amplitude of the oscillation becomes progressively smaller because of energy losses due to dissipative forces. Such oscillations are called damped oscillation. Every spring has its own damping and makes it stop eventually. If there is no damping in an oscillation system, it will stop if and only if an external force exerted on it. Thank you.
Assalamualaikum warahmatullahi wabarakatuh and good morning. My name is Nurul Izzati Husna binti Yusoff. Our objective is to determine natural frequency of the system at different mass. Second, to determine the decay rate of the system at 20 Newton for both upper and lower mass. Third, to demonstrate the DAISY lab in collecting data. The theory of our experiment is during free vibration, 2 degrees of freedom has two normal modes of vibration corresponding to natural frequency. This is our schematic diagram, and this is our free body diagram for M1 and M2. This is formula that we use to find theoretical natural frequency. Quantities under the square root of are positive. Hence, values are real for values omega equal plus minus omega 1 and plus minus omega 2. To obtain decay rate for each mass, the formula used is sigma n equals C over 2m, where n is for top and bottom of the mass spring.
My name is Cindy, and I'm going to explain about the procedure and the experiment setup. The first one is to define the spring stiffness manually using the test rig. Firstly, we use the 500 gram mass, and then we measure the original length of the spring, and then we change the mass into 10 Newton, and then we measure the length of the spring. This procedure is repeated a few times, and then the data is inserted in the Excel for us to find the spring stiffness. Excel, we find the spring stiffness by finding the gradient from the graph obtained. For our first objective, we determine the natural frequency of the system at different mass. So the first one, we use 20 Newton for both upper and lower of the system, and then we connect the accelerometer. It is connected to the NIDAQ, and then it is connected to the PC. Treated by changing the mass from the system, which is the first one is 20 Newton for both upper and lower, and then 10 Newton for both upper and lower, and the other one is 20 Newton and 10 Newton for both upper and lower.
For the NIDIQ, firstly we create new, and then NIDIQ makes MX test, acquires signal, analog input, and we choose acceleration. The channel is 0 for upper and 1 for lower, and then we rename for the channel 0, we change the sensitivity to 105, and then for channel 1 we change to 103, and we change the acquisition mode continuous sample for both channel, and then run stop and save. And then we open our DesiLab and we synchronize the DesiLab with our NIDIQ. And then we set our sampling rate and block size. And then we use scaling to convert the unit from G to meter per second square. After scaling, we use high-pass digital filter to obtain the acceleration data, and then we integrate twice to find the velocity and displacement. After that, the data is saved in the Excel. Meanwhile, the decay rate is obtained from the raw data by using recorder module. The data is then recorded and saved in Excel. As you can see, this is our natural frequency data. Okay. This is our decay rate data. From this data, we use the cursor to find the value from peak to peak. This is one of the example of peak to peak data. This is the data, and then the value is tabulated and the graph is obtained through Excel.
Assalamualaikum warahmatullahi wabarakatuh. My name is Khalid. Next, I'll explain about our results and also discussion. This is our results layout. This is the results for natural frequency when the upper mass is 10 Newton and the lower mass is also 10 Newton. Omega 1 for upper and lower mass is 1.82 radian per second, and omega 2 for both upper and lower mass is 15.9 radian per second. This is the graph for our natural frequency when the upper mass is 20 Newton and lower mass is 10 Newton. Omega 1 for both upper and lower mass is 2.27 radian per second, while omega 2 is 6.36 radian per second. This is the natural frequency graph when the upper mass is 10 Newton and the lower mass is 20 Newton. The omega 1 for both upper and lower mass is 2.27 radian per second, while omega 2 for both upper and lower mass is 13.64 radian per second. This is the graph for decay rate for lower mass. The value of the decay rate is negative 1.0924. This is the graph for decay rate for upper mass. The value of the decay rate is negative 1.0482. For the discussion part, the possible cause of error is because of the friction between spring and the rig might cause the decay of the system abnormally, and also the vibration of the loads caused by the screw that is not tightened good enough, causing the data reading become inaccurate. The decay rate of the top and bottom mass are different is because of the M1 is not equals to M2, and therefore decay rate top is not equals to decay rate bottom, since decay rate top is equals to C over M1 and decay rate bottom is equal to C over M2. Here is the calculation part to prove that the decay rate value is equals to the gradient of the graph ln x versus time.
Assalamualaikum. Hi, I am Nurul Najwa and I am going to conclude our experiment. As a conclusion, our objective, which is to find the natural frequency of the system at different masses and also to find the decay rate of the system at 20 Newton, are achieved. The value of decay rate for upper mass is negative 1.0482, and while for lower mass is negative 1.0924.
2, 3.
The natural frequency when both upper and lower mass is 20 Newton is 1.82 radian per second and 10 radian per second. Meanwhile, the natural frequency when upper mass is 20 Newton and lower mass is 10 Newton are 2.27 radian per second and 6.36 radian per second. The natural frequency when both upper and lower mass is 10 Newton is 1.82 and 15.90 radian per second. Meanwhile, the natural frequency when upper mass is 10 Newton and lower mass is 20 Newton is 2.27 radian per second and 13.64 radian per second. However, the theoretical value and the experimental value for both natural frequency and decay rate obtained are different due to several errors while analyzing the data.